Hi, I want to tell you a little bit about the complete graph, Kn. So what is this? The complete graph on n vertices is the graph containing an edge between every pair of vertices in the vertex set. So let's look at some examples of complete graphs. When n equals 2, K2 is the graph on two vertices with an edge joining them. So that's every possible pair, right, is connected by an edge. When n equals 3, we have 3 vertices. And then if I want to connect every pair, I'd need 1, 2, 3 edges. And for example, when n equals 4, if I wanted to connect every pair, so 1, 2, 3, 4 vertices, well, I have to connect the first vertex to all the others, the second vertex to the ones it's not connected to, the same for the last pair. So I get 6 edges there. Okay, so this is K3 and this is K4. So what kind of things can we ask about the complete graph on n vertices? Well, we might want to ask some questions like, what is the degree of vertex in Kn? Or we also might want to ask how many edges are in Kn. And counting the number of edges in Kn is one of those things. It's a combinatorial question, and there are lots of different ways of answering it. And that's what I want to share with you today, especially. So first, what's the degree of a vertex in Kn? Well, if I have n vertices, and I want each vertex to be connected to each of the others, if I have n of them, how many neighbors can one of them have? Well, there are n minus 1 others, and it has to be connected to each of them, right? So here, the degree of each vertex has to be n minus 1. And already that can tell me how many edges are in Kn. So I know that the degree, if, let's say, n minus 1. So if Kn is equal to a vertex set of n vertices and a set of e edges, then I know that if V is in V, then its degree has to be n minus 1. So if I look at the sum of all those degrees, I'm adding n minus 1 n times, because there are n vertices, and I know by my previous theorem on degrees of vertices that the sum of the degrees is twice the number of edges. So this tells me that the number of edges is equal to n times n minus 1 over 2. Okay, I think we've seen a sum like that before. So there's another way of thinking about this. Let's go back. Remember when I drew the K4, what I did was I said, okay, I'm going to start with one vertex and I'm going to connect it to 3 others in this case. And then when I went to my second vertex and drew in the connections, the edges that I still needed, I only connected it to 2 of them. And when I got to the third vertex, I only needed to draw 1 edge. So let's do that carefully below. So here's vertex 1, 2, 3, 4. If I want to draw in my edges, I have to draw 3 of them. If I start with sort of edges connected to 1, And then the edges that I haven't drawn yet are that are incident to 2. It's 2, 3, and 2, 4. And the edge, and then, oops, I should have put that 2 there. And then I only need one more edge, and that's this edge 3, 4. And 1 plus 2 plus 3, remember, that's equal to 6. And we had a way of thinking about this. If we want, so recall that if we looked at 1 plus 2 plus ... through n minus 1, we showed using induction in the last chapter that this is going to be n times n minus 1 over 2. Okay, and you can try that by induction yourself. I guess another way of thinking about this, probably better than what I just did, is you can think of Kn as follows. Well, let's do it with this K4 example. If I want to think about K4, I'm fighting with myself now. K4 is a K3, a triangle, plus one extra vertex connected to all of the edges. Okay, so K4 is equal to a K3 plus a new vertex of degree 3 that's connected to the old ones, right? So the old ones are the ones in the K3. All right, so if we think about this, then we can prove the formula for the number of edges in Kn by induction, right? So as a base case, we can see that K2 has only one edge, all right? And if we know that, if we know that Kn has n times n minus 1 over 2 edges for some n greater than or equal to 1, or greater than or equal to 2, we'll show Kn plus 1 has n plus 1 times n over 2 edges. Well, why should that be true? Well, let's think about what Kn plus 1 is. So consider Kn plus 1, and in this picture, I'm going to have a blob here. And inside this blob is a Kn. And maybe let me not start that way. So I have my Kn plus 1. It's some big graph. So consider Kn plus 1, and that's an and. And let V be one of its vertices. Okay, so if I draw it, I'm going to kind of single V out, and then V is connected to each of the n other vertices in Kn plus 1, and I'm going to think about that Kn as living inside that blob I drew. Okay, by induction, by induction, by the induction hypothesis, rather, Kn has n times n minus 1 over 2 edges, and I can see that the graph, that doesn't look very good. The graph Kn plus 1 has how many edges? Well, it's the edges in Kn plus, so it has edges in that copy of Kn plus the edges incident to V. And so there are n times n minus 1 over 2 edges in Kn and n edges incident to V. And if I find a common denominator, what happens? I get n times n minus 1 plus 2n, which is n times n minus 1 plus 2 over n. I factored out the n there, which is n times n plus 1 over 2, which is what I wanted. So there are all these different ways of seeing how many edges are in the complete graph. Okay, I'll stop there.